Okay, guys, solve this with me. So let's go through this step by step. We know we have a y. We only have vertical forces going downward, so we know there's a vertical reaction there and a vertical reaction at A. So let's right away turn this distributed load into a point load. So it's base 20 feet long. That's how much the uniform load is spanning times the magnitude, 20. So we got 400 pounds right dead in the center of this uniform load. I'm going to call it right here. I'm getting 400 pounds. This PLF stands for pound per linear foot. So keep that in mind. 400, so it's 400 pounds. And as you guys can see, we have a 20 pound-foot concentrated moment right here happening at 22 feet away from A. So I'm going to show you guys how to figure that out and how to incorporate it into your equilibrium equations. So let's start this sum of the moments about A. Now, it's important to choose what's positive moment and what's a negative moment. It doesn't matter, but I am used to choosing counterclockwise positive and clockwise negative. So I'm going to do negative 400 times the distance. It's happening halfway. This uniform load is 20 feet, so half would be 10. It's happening 10 feet away. Now, I see this 20 pound foot, it's happening counterclockwise. So I'm going to count it as a positive moment. And it's already in moment form, pound foot. And that's the units it's going to stay in when you're using it about when you're summing the moments. That's what you're doing with this 400 pounds. When you're multiplying this negative 400 pound times foot, 10 feet, it's the same units as this 20 pound per foot here. So let's keep that in mind. We're turning everything in terms of pound foot, in terms of moment units. So negative 400 times 10 plus 20, and it's happening counterclockwise. So I'm going to add it, and I'm going to do plus, what's this distance from B from A? It's 20 plus 12. I got 32 BY equals 0. So let's do the math. I got negative 400 times 10. Going to do the complete math here. So negative 4,000 plus 20 plus 32 BY equals 0. Let's do negative 4,000 plus 20. You guys can see that this moment is very small. This 20 pound foot is very small compared to the 4,000 pound foot that's happening next door. So I'm getting that plus 32 BY equals 0. So if I divide that by 32, I'm going to get BY equal 124.375 pounds, right? So 124 plus 3, let's call it 38 pounds. Okay, so let's sum the moments in the y. Negative 400. And as you can see, when you're summing the forces in the y direction, you don't take account in this concentrated load of 20 pounds per foot, right? You only take account the actual vertical forces. So I got negative 400 pounds plus 124.38 plus AY equals 0. So what am I going to get? 24.38, getting AY equal 275.62 pound. Let's put that over here, 275.62 pounds. And if you add 275.62 plus 124.38, you get 400 pounds as all your forces are equal to all the loading that's happening. So this beam right here is in equilibrium now. Notice how when you have a concentrated moment here and it's uplifting this part of the beam, it puts more force and more stress on the left part, which is why AY has a higher shear force, right, has 275, where BY has 124. That's because this pound foot is, even though it's very small, it still somewhat uplifts this beam. It's helping it pull it this way. That's why it's this moment is trying to pull this beam towards this AY. So that's why it balances out that way. And not to mention also too, the uniform load is basically on this more on this side as well. So that's another reason why AY is larger. But this beam is now in equilibrium. Thanks, guys.